Today, we're peering deep into what we've called the hidden engine of modern science. We're diving into array programming.
Which might sound super technical.
It does, but it's the absolute bedrock of numerical computation, really, across the globe. It's all about using this powerful, compact syntax for handling data, in vectors, matrices, and even higher dimensional arrays.
Tensors, right.
Exactly. And our focus today is on the library that made this whole approach foundational in Python, NumPy. So our mission for you listening is to really understand how this core open source library underpins, well, pretty much all modern scientific computing in Python.
And how it's adapting, because it's under some intense pressure right now from big data and all this specialized hardware we're seeing.
Yeah, that's a huge piece of it.
It's truly impossible to overstate NumPy's role. I mean, if you think of Python as the lingua franca of data science,
Which it is.
then NumPy is the underlying grammar. It's that solid, non-negotiable foundation that the entire scientific Python ecosystem is built on. I'm talking machine learning, astrophysics, everything.
And it's not just academic. The source material had some pretty incredible examples.
Oh, absolutely. When we talk about these landmark, high-profile discoveries in the last decade, NumPy was right there, in the engine room. For instance, it was a key part of the software stack used in the initial processing that led to the discovery of gravitational waves.
At LIGO, right.
At LIGO, exactly. And maybe even more visibly, the analysis that generated that first iconic image of a black hole.
The Event Horizon Telescope.
That collaboration relied heavily, on the principles of array programming, all executed through NumPy. This is how world-changing science actually gets done.
Okay, let's unpack this then. Because something this critical, it never just appears out of nowhere. Before NumPy unified everything, the source material tells us there was fragmentation.
That's the perfect word for it, a real problem. Before NumPy arrived in 2005, the field was basically split in two, and that division was really hampering growth.
So what were the two camps?
You had two main contenders. First, there was the numeric package. This was developed way back in the mid-90s, a true pioneer. It was written largely in C, which is key for speed, and it focused on really strong performance for small arrays.
And it found a home in places like, what, high-performance computing?
Exactly. Things like inertial confinement fusion research. But then its rival appeared, and it was designed to solve a totally different kind of problem.
The scale problem.
Precisely. You have these massive astronomical data sets coming in from telescopes like Hubble, and a team realized numeric just wasn't built to handle data that was larger than a computer's physical memory.
So they created a re-implementation.
They did. They called it NumArray. And it was this necessary evolution because NumArray added really important features like better indexing and, crucially, memory mapping.
Memory mapping. For you listening, that's basically a way to treat